Good day. This week's classes are on air distribution systems. And why are we studying them? Well, in commercial and industrial buildings, an air distribution system is used to supply conditioned air to zones and also to return the exhaust air. Now, looking at the supply system, what we do is we just generate a box for the air handler or the fan, and we draw a line for the main ducts, and then we just draw lines to the individual zones that are there. So that's the overall paradigm we use. And again, always recall there's a certain amount of outside air, and then that's made up by the return air as well to give the ventilation requirements. So what variables are we going to work with? One is the volumetric flow rate, that's in cubic meters per second. The duct length, which is usually specified. The duct diameter, which we will find. The duct velocity, which we'll also find, and there's limitations so it isn't too high. And then the duct pressure drop, which has to be matched by the fan pressure rise. How do we know the flow rate to a zone? Well, that's basically given from the open system first law. If we know what the zone load is, that again is a function of the number of people, what they're doing, equipment, and also environmental conditions such as sunshine that create the given zone load. And then the first law then just indicates that into the zone load we factor in the density, specific heat of air, and then the temperature difference. And the zone temperature will depend on the use. Typically I use 22 degrees C. And the duct temperature is something that you can vary. I've done research where I keep it nice and cold, 5 degrees C. Typically it's about 13 degrees C, but the lower you make this, the smaller you make the ducts. And again, air density at 1.18 and C sub P at 1.0. And again, just putting some numbers on this, and you can look at this in the notes, that basically for 15 kilowatts, a 12 degrees C temperature difference, that's about 1 cubic meter per second. And as I've said before, we know Q from the zone occupancy rate. So now let's go ahead and take a closer look at the zone pressure drop. We put this graph down at the beginning of class earlier in January, where we have pressure drops due to the duct friction, linear with length, and then any of the fittings that are there will create a pressure drop as well. So what you do is have a overall duct friction equation with the friction factor, length over diameter, density, and velocity squared. We use, and I got this directly from the fluid mechanics book, if we know the Reynolds number, roughness, we can get the friction factor for turbulent flow. Typically, I just use 0.02 as a starting point for my calculations. And in the homework problems, I've just said, just keep it at 0.02 or so we don't have to iterate back and forth. The Reynolds number is the typical value where it's 4 times the flow rate over pi, diameter, and viscosity. Again, if the Reynolds number is above 2300, it's turbulent flow. And if it's less than that, it's laminar flow, and there are equations for that. So this is something that you've done equations with before. Now, with the fittings, then what we do is we assign a fitting loss coefficient, and that coefficient is dimensionless, and we multiply it by the velocity pressure, rho v squared over 2, and the K values for the fitting coefficient depend on what we have. Entrance, contraction, expansion, a diffuser, and then a T. And in the homework problems, I'll specify just one T, 0.13 coming across, and K is a 1.2 going back. So for the duct design, we know the duct lengths because that's a function of the architectural layout. You just measure those. The volumetric flow rate, Q, We know that from the use patterns of the room, but we don't know the duct diameter. So there's a number of design methods. The two most popular ones are equal friction and static regain. I like to use equal friction. And all that just says is the friction pressure loss per unit length is fixed. You pick a value, and then with that, you can go ahead and solve iteratively for the pressure drops in each duct system, including both the fittings and the friction loss. And then once you know that, then you can multiply the pressure drops by the flow rate to get the total power required to move the air to the duct. And finally, this is what you can do for homework. I simplify things by choosing a constant friction factor. So you choose a value of the pressure drop unit length, basically somewhere between 1 and 4, 1 and 5. For the homework, I specified what it should be. And then I've also said pick a constant friction factor. And if you do that, you can then take that equation for the pressure drop per unit length and recast it using the continuity equation, where if you know the flow rate, you then know the diameter for a given friction factor, pressure drop per unit length, and density. So for example, if the friction factor in this case is 0.08, density of 1.18, delta P over L 3, and around 1 cubic meter per second, that's our example we had earlier, the pipe diameter is 0.36 meters, or about a foot. So I hope that helps you out. Bye for now.